Sponsored by Coca-Cola.
What was it before Dr. Pepper?
Yeah.
Okay.
Didn't hold that money.
Okay, so let's talk about all of like number 4. Because if number 4A is wrong, everything else is going to be wrong. So, I beg of you, do not get wrapped up into the equations game, okay? It is going to lead to pain and despair. You have to think the problem through. So, before you even start on anything, okay, look at this. Here's this ball that's going to go up, and it's going to come back down, and it's symmetrical, right? It's symmetrical. Jones can get this. So we're playing along. So, the total flight time is, what, 4.4? So how long did it take to go up?
2.2.
2.2. So my time up is 2.20 seconds. What's the sign of my initial velocity? Positive. So I know on my velocity time graph, I'm going to start with some positive velocity, and this line's going to do this. Figure out what's going on before you even go to an equation. Okay? The worst thing that you can do is get this problem and go, oh, what equation am I going to choose? Bad. It's going to be a train wreck tomorrow on the test. Think the problem through. Where's the ball at this point when this crosses 0 meters per second? That's the maximum height, right? There's your max height. Now, you know the slope of the line. Logan, what's the slope of the line? Beautiful. Why? Due to gravity, right? This big rock that we're on, all of us are attracted to the earth. Boom, here we go, right? This is the acceleration caused by gravity. So basically, I'm trying to figure out what velocity I have up here so that at 2.20 seconds, my velocity is 0. So think of this in terms of money. You're showing up at the mall and you're told that 2 seconds, basically about 2 seconds later, you're broke and you're spending $10 per second. Roughly, how much money did you walk into the mall with?
20.
About 20 bucks. You walked in with about 20 bucks. Every second that goes by, you're spending about $10. It's going to take about 2 seconds for you to go broke. So you had to walk in with about 20 bucks. That at least gives you a ballpark answer to start with. Okay, hey, this answer is probably going to be around 20 because I'm spending $10 per second. Okay? So, look at this. Now that you kind of know what's going on, now you can go, oh, okay, right. V equals V naught plus AT. Here's what you have to be careful of. You're searching for V naught. You're trying to find this y-intercept. That's what you're searching for. You know the acceleration, you know the time is 2.2, and you know the final velocity is going to be 0. Then it's just a matter of solving for V, and again, solve this equation. You got V minus AT equals V naught. 0 minus negative 9.8 times 2.2. So your answer to 4A should be around 21. Okay, because if that's wrong, everything's going to be wrong. Literally, everything else is going to be wrong. So, you're up here, you're going to 0. Now, this is about terminology. If I start with a speed of about 21 meters per second, when it lands, what's my speed going to be?
20.
About 21, because 21, just how fast you're going without any direction is just speed. Now, but this is the difference between velocity. If I start with a velocity of 21, what velocity am I going to land with?
Negative 20.
About negative 21. So you have to understand the terminology. So when you throw something up in the air and it comes back down, the velocities, if it's symmetrical, that's a huge if, are going to be the same value, opposite signs. The speeds will be the same. Okay? The speeds will be the same because that's just how fast you're going. Okay? So, when you get to 4D, your position time graph is going to look something like this. All I'm asking you is what's the slope of the tangent lines? Slope of the tangent lines on a position time graph is the magic code for what?
Velocity.
Velocity. How fast is it going? At time 0, what's the velocity of the object?
21.
About 21 meters per second. Okay? Don't tell me it's 0, because if it's 0, it's not going to go very far. Okay? So basically, I'm asking you, what's the velocity at all of those points? That's all I'm asking you. That's it. Now, when you get to the question about the Enterprise in Columbia, okay? Let's talk about that for just a second. So, you have two ships that are at the same point, okay? One's traveling 600 meters per second. The other one's traveling at 450 meters per second. Tori,
Yes.
what's going to be the sign of the acceleration from these two ships?
Negative.
Why?
Because
Because
it's slowing down.
with
The velocity.
beautiful. Okay? So again, on your velocity time graph, one of them is starting at 450 and the other one is starting at 600. Okay? That's what you got. So you're going to stop, they're going to go out, they're going to change direction, they're going to come back. So what does their velocity have to do? Well, three things does the velocity have to do.
Slow down.
Stop,
Slow down.
stop, slow down, stop, and change sign, and then speed back up, right? So this is what's happening here. But here's the question. Does that take 86 seconds or 43 seconds? 43, because the entire time to go out and come back is 86. Okay? So this is going to take 43 seconds for it to go out, stop, come back. So basically, that's going to be 43 seconds. So, you know the initial velocity, you know the final velocity. Okay, so there's no difficulty, we're back. So, both of your accelerations on number 8 should be negative values and both should be between 10 and 15. Everybody cool with that?
Yeah.
Okay. On your velocity time graph, make sure that you label both lines. Now, when you get to number 9, and I promise you, there is going to be a problem like number 9 on the test. You mark my words. It's going to be probably the second to the last problem on the test. So, if all goes well on number 9, your acceleration should be around 95 meters per second squared. Which is a pretty decent acceleration, okay? But you're not firing the engine for very long, okay? So then your time should be less than a second. So in other words, we're going to fire this engine for less than a second, then we're going to shut it off. So here's what you have to be able to visualize on this problem. Your velocity time graph, because in this situation we're actually keeping track of when, starting from 0. On this problem, your velocity time graph is going to start at 0, and then it's going to go up to like 75 meters per second. So that's like me throwing this ball up in the air at 75 meters per second. So shutting off that engine is the equivalent of this ball leaving my hand. So me throwing it is like when the engine is firing. As soon as it leaves my hand, what does it start to do? Slow down. So this graph immediately will start to slope down like this. So where is the rocket at that point?
It's maximum height.
It's maximum height, right? So this is where you shut off the engine. So here's the deal, and this will play out large when we get into forces. To change the slope of the velocity time graph requires you to change the acceleration. The only way you can change the acceleration is if you change the force acting on the object. So we went from having the engines providing a positive force to shutting that off, and then gravity is providing a negative force, which is creating a negative acceleration. So we're going from 0 to 75, and then 75 back to 0. Okay? So this time is going to be less than a second. Then you're going to figure out the time that it takes to go to 0. And I'm going to tell you this on the graph tomorrow on the test. Make sure that you keep like a running clock. Okay? So it's going to be this amount of time to get it up to speed, and then you're going to add to that the time that it takes to go to 0. Okay, that's the only way you can have a slope that's negative 9.8 meters per second squared. So if all goes well, on number 9, your time for it to stop should be around 8 seconds. Okay? Everybody cool with that one? Hunter?
Not sure what equation on that.
For which one? On that second part?
Yeah, it's like
Okay, look. How fast are you going when you shut off the engines?
450 or.
No.
Oh, sorry.
75.
You're going 75, right? When it reaches its maximum height, what's the final velocity?
0.
0. Do you know the rate at which it's slowing down? Negative 9.8 meters per second squared, right? Because that's gravity is what's making it slow down.
V equals V minus H.
Yeah, there you go.
So this loop around-
There you go.
So that's just.
That's it.
Initial velocity.
Yes, ma'am.
On 9, the time should
This
be less than
one,
a second.
I just.
On 9, that first part of 9 is, yes.
Oh,
The second part, no.
No.
The second part is, no.
Whoa.
On the, I was talking about to go
I do
to reach
acceleration
maximum
time
height.
to time.
No, that's what I was
So
referring
if
to.
we're
Okay,
going to
okay.
use add
Because I already said that
acceleration
first time
which
is
at 1
less than a
second,
second.
Okay.
This time is going to be a little bit less than 8.
21.6 plus
Yeah.
negative 9.8.
Yeah,
No, we were like, it's so wrong.
No, Mr. Burkett, whoa, stop, this is horrible.
Okay, yeah.
Okay, now,
Feel way better now.
make sure on your mini lab,
Okay.
okay, show me the calculations because everybody's data is different and there's different ways that you can solve this problem. So, honestly, the first time I lose track of what you've done, I stop grading at that point. This is not about an answer, this is a process. So this is how I would tackle the mini lab. This is just me. You know your velocity time graph is going to look something like this. You know that's what it's going to look like. You know that this time is going to be half the time. Let's say it's 1.20 seconds, whatever half the time is, okay, whatever it is. You know this area because you know how high it went. And then you know, oh, area of a rectangle is 1/2 base times height. You know your base because you're going to know half the time. You're going to know the area because you're going to know the maximum height. What you don't know is h, which is going to represent that initial velocity. Okay? Then you're going to find the slope of this line. Then you do the same calculation over here, but you're just going to use a negative displacement. Okay? What's the only time you're going to use negative 9.8 meters per second squared?
Calculating experimental error.
Yes, ma'am, Madeline. Yes, ma'am. So, honest,
It's okay to have a negative experimental error.
no, it's an
right?
absolute value.
Yeah, you have this. It's
But when you divide it by negative 9
no, but
point.
it's the absolute value of that entire.
It's
thing,
the-
Oh, is
not
it?
just the
Okay.
top.
The whole thing is an absolute value.
Okay.
Okay. Anything else on that assignment? Once, twice, so.
For the second part of 9,
Yeah?
what's like the rough estimate for the acceleration?
Mike,
Yeah.
there's nothing to calculate. You shut off the engine. What's making it slow down?
Gravity.
What's the acceleration due to gravity?
Negative 9.8.
There's nothing to calculate. Probably, so your answer should be around negative 10. How about that? Okay? If you're not sure, ask Olivia. She knows. All right, so the slip of paper that I gave you, here's the situation. Here's a building that's 8 meters tall. The ground is the reference point. You're going to throw a ball up 12 meters per second, and then it's going to fall all the way back to Mother Earth. Okay? So this initial velocity here is 12 meters per second. So you're here, it's going up, it's going to fall all the way back down here, starting 8 meters off the ground. Some perspective, this ceiling is about 2.5 meters tall, so you're up in the airways. Okay? So here's the setup. There's a whole bunch of things that you're going to have to find, like the time up, and then you're going to find the time down. You need to find the maximum height, and then also at some point the velocity at impact. Okay? So, you need to figure out how long it takes to go from here to here, how long it takes to go from here all the way down to here, how high that thing is above the ground, measured from the ground, and then how fast it's going at the point of impact. Now, I'm going to give you about 10 minutes to work this problem. This will tell you and give you an idea of how you are for the test tomorrow. Because here's what's going to happen on the test tomorrow. There's two things that will happen. The sun's going to rise in the east. The last problem on your test is going to be a problem like this. Okay? It's going to be worth more points than any other problem on the test. I promise you, there is going to be a problem like this. Okay? Mark my words. Okay? I write the test. I know what the last question is going to be. So, work this problem, and then if you're feeling good about a section of this, whether it's the time up, the time down, whatever, come up here, write it on the board. Now, there's a whole bunch of different ways to work this problem, okay, depending upon your preference. There's a whole bunch of different ways to work this problem. So if you come up here, I want three things. I want the solved equation for whatever variable it is, whether it's time, velocity, height, whatever. So I want the solved equation, then I want that equation written with the numbers, and then I want the answer. Okay, so I want the solved equation with the numbers, and then the answer. So when you're feeling good about either the time up, the time down, max height, or velocity of impact, come up here, write the equation, write the numbers, put the answer. Now, like I said, and there's different ways that you can do this problem. Okay, there isn't a set, oh, this is the only way to do it. There's probably 10 different ways that you can solve this problem. Okay, so I'm going to shut up. You take about 10 minutes, try and figure this out. So, Mad Max. Okay, so when you look at all this, here's what I'm going to look for on the test. It isn't just going to be 1.77 and 1.22 and all the distances and all that good stuff. I'm also going to be concerned about the process, okay? So, and this is what I like. So if you look at like this time up. So here's the solved equation, V minus V naught over A. Nice. This is the quality of work that I expect to see. Now here's what's important. First off, even before you did any calculations, Felix, why did I know my time up had to be more than 1 second?
Because is it because how tall the building is? No, I don't know.
Felix, let me ask you this. What if my initial velocity had been exactly 9.8 meters per second? You go to the mall and you have exactly $9.80, and you have to spend $9.80 a second. How long is it going to take for you to go broke? 1 second. Now, I've given you $12, and you have to spend $9.80 a second. Is it going to take you more than a second to run out of money? Okay? Because again, you have to understand what these slopes mean on a velocity time graph. So this acceleration means that for every second that goes by, your velocity is going to go down at a rate of 9.8 meters per second. So on your velocity time graph, let's go ahead and jump to that. So your velocity time graph is going to start here at 12 meters per second, and it's going to go like this. So, well, and again, you have to understand what that acceleration is. It says for every second, I'm going to drop 9.8. So since I started with a velocity that was greater than 9.8, I know I'm going to take more than a second to reach a velocity of 0. So, Madeline got that time of 1.22 seconds. That's my velocity time graph. That slope, I know is going to be negative 9.8 meters per second squared because that's the acceleration due to gravity. Life is good. So, here's what you don't do. Okay? Don't sit here and just write down 12 divided by 9.8. Okay? Yeah, are you still going to get 1.22 seconds? You will. But here's the bigger picture. You're trying to convince me that after all this time, you really understand how physics is done. that you realize this is going to be a consistent methodology on solving this problem. I'm going to go from 0 to 12 with an acceleration of 9.8 meters per second squared. That's going to take me 1.22 seconds. I'm more concerned about this than I am this, okay? That's why you're going to have an entire page to work this problem, okay? All right, so there's my time up. Seems reasonable, a little bit more than a second. My velocity was a little bit more than 9.8 meters per second. Hey, we're in the ballpark, okay? Now, let's talk on the time down. So, actually, let's skip that. Let's go over here to this maximum height, because you've got to have this before you can have this. Now, bonus, who did this? Who did this one?
Mary.
Mary. Okay. So here's again, this is what I'd like to see. Here was the solved equation. I got 0 squared minus 12. And some of you are like, when you have this, some of you are like leaving this out. This has to be 0 minus this quantity, okay? Or otherwise you don't get, or otherwise the signs don't work out. So this has to be 0 minus 12 squared. Now, here's what's important. Mary, just like Madeline did, she's got that negative 9.8 down there in the denominator, just like we did over here. You cannot have this as a positive value. This has to be a negative number on top divided by a negative number. She got 7.35. Now, here was the one tweak that we had to do. This has 3 significant digits. This is a calculated value. So your given value had 2 decimal places to the right, that 8.00. So that's why she could write this as 15.35. Because remember, when you're adding values, what do you worry about? The number of significant digits or place value. When you add,
Place value.
it's place value. So that's why this ends up at 15.35. Okay? So that's one of the subtle things that you need to watch for. So, now, you got this number. Is there another way that you could find the maximum height? This is just one way. Is there another way that you could find the maximum height? Yeah, if you look at your velocity time graph, look, you know that's 12 meters per second, and you know this is time is 1.22 seconds. You could find that area underneath that velocity time graph and then add that to 8 meters. And you're still going to get the same thing, okay? Or maybe within 100, okay? But it's basically going to be the same thing. You could also use distance equals 1/2 at squared plus v naught time. Plug in the 1.22 seconds. Plug in your acceleration. Plug in 12 meters per second. You could also do it this way. That's why I said on that maximum height, there's like a whole bunch of different ways that you can do this. But, right?
Is the reference point the ground? Not
Yes.
the open?
Yeah, that's the reference point. That's ground zero.
What if you were just to make the reference point the building?
Well, you could, but
Would that affect, like, would that be wrong?
yeah. Because then it's going to get real ugly, because then your displacement is going to be like some positive number to 0 and then down to some negative number. You could do it, but it's just going to be a god-awful amount of extra work that you don't want to. Okay? All right. So, but here's the disadvantage of using the velocity time graph, or distance equals 1/2 at squared plus v naught time. All of those are dependent upon this time. If this time is wrong and you use it the next step, then that's going to be wrong. So the beauty of what Mary did is that this goes off of known values. You're not dependent upon the time. So we're at 15.35. Now, here's the thing. Basically, at this point, it becomes a separate problem. We're saying that this thing is going to start here, and we're at 15.35 meters tall, and we're just going to drop it. Okay? So how it got to that point doesn't make any difference. This just is falling for 15.35. So if you've not embraced this equation to find time down, embrace this equation. Okay? This is a cool deal. This is the simplest way to do this problem. So here's what's important. If you look at what Honus, you did this one, right? So again, this is what I'm going to look for on this problem. I'm going to look that you have 2 negatives underneath that radical. Okay? That's one of the most critical things I'm going to look for, is that do you have 2 negatives underneath that radical? Because if not, I'm going to snarkily write, ooh, imaginary time, cool. Okay? Bad. No, don't. Okay? Now, I got the 1.77, so the total time is gonna be what?
2.29.
2.99, okay, so that's gonna be my total time. So now, I can come over here, okay, and go, oh. Get back here. That's gonna be at 2.99 seconds. Now, when you draw this graph tomorrow, and you're gonna draw a graph like this tomorrow, if you get to this point and you're trying to like change the slope of this line, you have done something wrong. We okay?
Yeah, I'm sorry.
Okay,
I was hot to fly.
okay. So, if you're drawing this line and you want to change this slope, don't. Something's wrong. Because this slope should be negative 9.8 meters per second squared the entire time. Because if you change this slope, you're changing the gravitational field of the Earth. Cool, probably not going to happen. Let NASA know if you do. Okay. So, on this velocity and impact, we got 2.99 seconds. We got negative 17.35. Now, here's what's important. Here's what's important. And this is nice what Bree did. So, she used v squared equals v naught squared plus 2ad. Because she took the square root of this, she had to realize, hey, I've got to choose the negative root. Okay? And that was one of the nice things that she did coming out of this. She chose the negative root. Because your calculator is just going to give you 17.35. You've got to choose the negative value for that. Now, this is one way to find the velocity of impact, and it's cool. But here's what you have to be careful of. If you're going to start with that initial velocity at 0, you have to use the entire length of the distance that it falls. You could actually do this and start with 12, but if you're going to do 12, then your distance only has to be 8 meters because it's going 12 meters, negative 12 when it crosses this point. So you can use this and start with 12, but you can only use 8 meters. You're going to get the same answer, okay? But, so I don't care how you do it. Did somebody else find the velocity and impact a different way? Ethan, what'd you do?
The v equals v naught plus 18.
Okay, so you used v equals v naught plus at. What did you set v naught equal to?
0.
What did you use for your acceleration?
Negative 9.80.
What did you use for the time?
1.77.
Okay, now, Ethan did was cool, and it's nice, because he's basically saying, I'm going to my velocity time graph, and this thing is going to start at 0. And then it's going to fall for 1.77 seconds, and then I'm going to find my velocity that way. Okay? That's cool, it works. So the advantage of what you did is that this will automatically generate that negative sign in your velocity. You don't have to remember to choose the negative root. It'll automatically generate that value, okay? That's an advantage. Now, you could actually go and set v naught equal to 12, okay? If you do that, and you can, and it works. Whoa, wrong way. You can set v naught equal to 12 is your y-intercept, but then you've got to use the entire time of 2.99 seconds to get to this point. So you can start with a v naught of 12 to get your final velocity. You just have to use the entire time. Okay? Yes?
So should velocity and impact be negative?
Yes. Because you're down here, it's going down, and up is defined as positive, and down negative. It has to be negative. Otherwise, it doesn't make any sense. Great.
So you said for like the time down, you can do velocity initial, so it'd be like 0 because it
Yeah.
stopped at the top, and then you can do like final as negative, like what was it, 12? It's negative 12, and then find that time, and then add it to the time if you have a velocity initial of negative 12, and then a final of like 0, I guess.
No.
Or I guess you already-
You can do this, but you are going to go through a god-awful amount of work.
Oh, okay.
Don't.
All right.
Okay, don't. You can do it, but don't.
Okay.
Because what you have to do is sit here and go, okay, at this point I'm going to 0, and then you're going to be at negative 12 when you cross 8 meters, and then you have to figure out how much time it takes to go from there down from negative 12 or 8 to 0, and don't.
Okay.
Don't.
Yeah.
Don't. Now, so I promise you, like I said, on the test tomorrow, you're going to have a problem just like this. The only thing I'm going to do is change the numbers. That's it. Nothing else. Okay? There's going to be a problem just like when you get done. If you haven't done all these steps, you have done something wrong. On the review, I'm going to have a problem like this. You're going to have the answer key for it. You know you're going to have this problem. You work this problem again. You go home, you take that sheet, you work that problem. Then you change the numbers, and then you work it again. And then you say, wow, what could I do differently? Maybe you say, well, maybe if I drop a ball straight down, well, how long would that take? Oh, okay. Do some variations on the theme. What if I throw it faster? What would that do? Okay. What if I just drop it? What would that do? Okay. Then you take the review, and then you work that problem. And you make sure that you can do this. And when you're working this problem tomorrow, this is how you want to do. You want to keep this thing all laid out. Time up, time down, max height. Keep everything labeled. Because keep in mind, tomorrow night, I'm going to have to grade 51 of these. And if you think I'm going to go through and find random numbers that you have written down and try and guess what they mean, no offense, you're nuts. It ain't going to happen. Okay? You keep this very organized and very neat. Now, let me kind of give you some ideas of some other things that might be on the test in terms of just like a practical situation. So let's say that you've got a hill and you've got an object that's rolling and it's going to go up the hill. And let's say that uphill is defined as positive. So when that thing starts up the hill, first off, what's the sign of its velocity?
Positive.
Positive. So I'm going to have positive velocity. What's it going to do as it goes up the hill? So what's the sign of my acceleration going up the hill?
Negative.
So I'm going to have negative acceleration. So which direction are my acceleration vectors going to point? Down. So I'm going to have my velocity vectors are going to be getting smaller, going up, which means my acceleration vectors are going to be pointing downward. Okay? Now, once it reaches the top of the hill and starts to roll down, now what's going to happen? Velocity vector is going to be pointing because it's going to be, and so what's the direction of my acceleration vector? Down. Okay, because now I'm going to have that same acceleration. So what would the velocity time graph for this situation look like? Start up here at positive and it would go through something like this. Where's the cart at that point? Highest point. And then it's going to be speeding up, rolling down the hill. So be able to take these ideas and work with them in different situations. You know you're going to have a rocket problem. Okay? So you know that's going to happen. Okay? You are going to have a rocket problem. Make sure that you know how to work that problem on that assignment. You know the last problem is going to be a ball off of a building. It's going to happen. Okay? So stop that. Let me hit out some stuff. So here's the story of Benny and the chicken.
Yes.
So,
Like and subscribe for
in
more.
about all of Africa, especially southern Africa, you have what's called the traditional healer, okay? And it's more of a spiritual experience when you go to these guys. It isn't just, hey, let me listen to your heartbeat, run some tests. So typically what happens when you go to a traditional healer is that he's got like a bag of bones. Okay, literally, like it might be from a gazelle or something. It's a bag of bones. And so he lays out this leather parchment on the floor. And then he takes these bag of bones and he takes them in his hand. And he blows on them to impart his spirit on the bones. Then he gives them to you. And then you repeat after him. It's usually in Setswana. You don't, unless you're really good at Setswana, you don't know what it is, but you just repeat the words and move on. And then you blow on the bones to impart your spirit on the bones. And then you throw the bones on the parchment. Okay? And then he gets down and it's called reading the bones. So how the bones land and where they land tells him what's wrong with you. So he doesn't take your pulse, he doesn't do anything, he reads the bones. And he'll say, oh, you're having migraines, or you're having liver problems, or your arm has been severed, whatever, okay, based upon the bones. Now, the power of the human mind to heal the body is incredible. And you all sit there and go, whatever. It's like, no, people there believed they were going to get better. Unless it was something terminal, this worked a surprisingly large number of times because people thought that they have faith in the traditional healer. And you might say, oh, here, rub this on your forehead or whatever, okay? But people believed they were going to get better. So, that's the background. So, Benny, at the school that I taught, all the kids, the school that I taught was like sophomores, juniors, and seniors in high school, okay? So it's kind of like your level of class. And the sophomores took all of the classes. They took agriculture, science, math, English, Setswana, history. And then when they got into juniors and senior years, then they specialized within that area. So the sophomore years kind of showed them everything and they could find out what they're good at. So one of the classes that all the sophomores took was agriculture. And everybody had like a 4x8 plot of land that you would grow crops on, kale, corn, whatever. And so Benny was the gardener. So Benny maintained this garden. He would do the watering. He would maintain the fence around the outside so the goats didn't get in. And Benny, when I was there, was probably close to 60. And Benny was the nicest guy in the world. He didn't move very fast. Benny had done his time, right? Okay. Always wore like the green rubber boots that came up to about here. And he always had like kind of a long coat on, even in the heat of the summer. And Benny, and he'd always smile. Benny, how you doing? How do you do that? Okay, I can't think. Great guy. So, a friend of mine in the Peace Corps taught in Francistown. Francistown is like the second largest city in the country. And so, a lot of times I'd go in there because that's where I'd go to buy groceries. Because I lived out on the outskirts, kind of in a remote village. So I'd go into town, I'd stop, and I'd see Mia, her name. She was from Buffalo, New York. And in Botswana, the teachers lived at the school. So it was weird, but this is just because of the housing. So she was living with the Botswana guy in the same house, okay? They had separate bedrooms, and don't flip on. Oh my God, they were living together. Okay, it's okay. And this guy was named Nick, and he was a nice guy. He taught science, and Nick and I would have these great conversations. He was from Botswana. And so we'd have these great conversations about science and how science is taught in Botswana versus how science is taught in America. And we'd have these great conversations. And so I stopped there. It was like on a Friday night. And I said, and I talked with Nick. And he goes, hey, I got to go out to your school tomorrow. And I said, why are you going out to Shawshane River School? Because it was like a 20-minute drive. He goes, well, I got to take another teacher and her daughter out to see Benny. I said, Benny? Like the gardener. He goes, yeah. So why are you taking Benny? Why are you taking a fellow teacher and her daughter out to see Benny? He goes, well, the teacher's daughter was like 6 months old. Daughter had been basically sick since she was born. They've been to the hospitals, they've been to the doctors, they can't figure out what's wrong with this girl. She's been sick basically since she was born. And so Nick says, hey, we're going to take her out to Benny because Benny is a traditional healer. I said, Benny the gardener. He goes, yeah. He goes, you don't understand. He's one of the most well-known traditional healers in the country. Like members of parliament go to Benny. I said, Benny the gardener. He goes, yeah. He is just known throughout the country as one of the best traditional healers. He goes, the woman's at wit's end. They can't figure out what's wrong with the baby, so we're going to take the baby out to see Benny and see if Benny can, figure out what's wrong. Okay, not a big deal. So I see Nick like Saturday afternoon. I said, how'd it go out at Shawshane River School? He goes, well, Benny couldn't help her. I said, why? He goes, well, he needed a live chicken. I said, seriously? He goes, yeah, we didn't have a live chicken. So we got to go back after we get a live chicken. Now, there was a Kentucky Fried Chicken in Francistown. I said, you guys couldn't take out like a box of Kentucky Fried Chicken and call it good? He goes, no, it had to be a live chicken. Okay, whatever. So about a week later, I run into Nick. I said, Nick, what's going on with Benny and the baby and the chicken? And he goes, Stan, I have no idea what happened. All I know is that the baby is healthy and the baby's been fine. I said, what happened? He goes, here's all I know. Benny took the chicken and the baby into a room for half an hour. The chicken's dead, and the baby is fine. He goes, what happened in that half hour? I have no idea. But the baby's been healthy ever since, and Benny did his magic. And he goes, the chicken's dead. So that's the story of Benny and the chicken. And so it was like, ever since then, it was like, wow. You know, so that was like right before I left. And so it was like, wow, Benny, yeah. So I have no idea what happened to the chicken, but the chicken's dead. So there's the story of Benny and the chicken. So it's like, okay. Anyway, so you got the rest of the time, work on the review, chill out, whatever. Okay.